Thank you, Jamia. Hello, everyone. My name is Brad Russell, and I'm a principal geotechnical engineer at BGC in our Vancouver office. My area of practice has focused primarily in tailings design and management, and I currently serve as engineer of record for 2 tailings facilities. And so the upcoming topic is of interest to me as risk-informed decision-making becomes more common in the tailings industry, but it's also becoming much more expected within tailings design and management practice. And while the practice of reducing risk is not new, and our design process has always strived for this, there's increasing demand for quantifying risk to help inform and justify decisions. And there's well-established methods for quantifying risk, like failure mode analyses and semi-quantitative risk assessments. But we see there's also benefit from development and adoption of screening level tools that can help inform risk characterization through more streamlined methods. And our next topic with Meg McKellar is going to walk through some components of an approach we feel can help with this by helping to identify key risk driving scenarios, which can then help inform where to direct our more focused efforts of detailed analyses. Meg is a junior geotechnical EIT who joined BGC in March of 2024 after completing her PhD at Queen's University as part of the CanBreach program. Her research focused on strengthening industry practices and informing numerical modeling with insights gained from physical experiments, including construction and controlled failure of 1-meter tall dams. At BGC, Meg contributes to geotechnical fieldwork and numerical stability modeling across several active projects, with a strong emphasis on keeping research at the forefront of design and investigation. Over to you, Meg.
Thank you, Brad. So good morning, everyone. Thanks for joining. I am talking today about our proof of concept probabilistic inundation model of tailings dam breach release volumes. And so I want to start by asking the question, why do we conduct tailings dam breach assessments? Or even what is a tailings dam breach assessment? And so we undertake these studies so that we can evaluate what the incremental consequence of a dam failure could be. So that's going to be, what damage do we have to be concerned about that's going to be caused by failure? And so this assessment is often based off of a credible failure mode, which would be a failure mechanism that would be physically feasible for the dam, given its characteristics and its surrounding environment. And these baselines of practice are provided by both the Canadian Dam Association, the CDA, and as well as the Global Industry Standard on Tailings Management, the GISTM. And so when we boil it all down, what we're really trying to do is build a picture of risk that is posed by a tailings dam. And so in the GSTM, along with in other standards, what they're really calling for is the need to incorporate these better risk management strategies when we assess tailings structures. However, when we estimate that there's over 35,000 tailings dams globally, how do we even begin to try and adopt these guidelines? And so therein lies our overarching goal, and the objective of the work is that if tailings management is in need of more risk-informed decision-making, let's try to start to build those right tools to do that. And so our goal is to develop a range of tools in the team to help enable a better understanding of risk and also improve decision-making for the safe management of tailings. And when I discussed the intent of these tools and these screening level analysis that we're going through today, I just want to mention that they're in no ways meant to substitute or replace these rigorous methods that we have for tailings dam breach analysis, or to replace expert-based decisions that we're using in these quantitative analysis. Their intent is really just to complement the practice so that we can accelerate the adoption of risk-informed decision-making. So an example of that could be that we have multiple sites we want to assess, and we could run these screening level tools so that we could understand from a risk prioritization level where focus should be drawn. When we discuss risk, we often break it down into this equation where we can understand that there's a probability of failure, but there's also an associated consequence. And this work really started by a paper in 2023 by Porter et al. That understood that the probability of failure for a tailings dam could be understood through both historical methods and also a good level of professional judgment. So where the work that I'm going to show today is going to focus is more on this consequence side. So the standout variable when we really think about consequence is going to be the volume of material that is able to leave the facility. And so when we could consider that while there's a probability of failure inside this risk equation, there's also a probable associated volume that could be given. There's an associated probability that any given volume could also leave the facility. And where this started was with a screening tool to understand the probabilistic distribution of release volumes. And from this, it took understandings from empirical relationships as well as those that are built from physical and geometric analysis and combined them to build a baseline probability distribution for outflow by failure mode. And so this Lin et al. 2022 paper provides a really nice figure to highlight this, where we can understand that from a breakdown of historical events, foundation failure, so highlighted on the left, has historically had a higher percent of release volume compared to that of overtopping failure on your right. And we can use these comparisons and this data to help in our screening tool. And so what the team did was fit a beta distribution to this data set. And why did we use a beta distribution? Well, what we currently have on screen is really an average of the historical conditions for any given failure mode. But what is an average tailings dam? And so there's likely no one answer to what an average tailings dam could be. They vary based on the volumes they retain, the height of the dam, or even if they have the potential to liquefy. And so what the team did was break down these topics into 4 site scaling factors. Those are going to be the release potential, the liquefaction susceptibility, the pond ratio, and the dam type and fill configuration. And so using this, we can assess these scaling factors for a dam and create an overall scaling factor that is site specific and apply that to our beta distribution. So this now gives us the opportunity to scale our data and to add in some flexibility into its interpretation. So for example, if I had a dam that was susceptible to liquefaction, I could have an increased scaling factor, and my beta distribution could be pushed maybe to more of this red dotted line that we're seeing on the plot. And the output from a result of scaling our beta distributions could be something like this. Where as an example, we have the proportion of the total stored volume that could be released, and I could take an understanding of what my 50th percentile of volume release could be, or my 95th. And I could take this singular number and I could put it into my breach modeling and receive an output. But that's only going to be one outcome, and we're building this model so that we can get a probabilistic tool, something that we can assess many potential outcomes from. And so our next question was then, is there going to be an inundation model where we can rapidly simulate the range of release volumes that we've considered without the need for a proper hydrograph? And that's where we turned to ProDF. And so in short, ProDF is a progressive flow routing tool that allows us to rapidly assess flow inundation, and it was previously used for a lot of debris flow studies. And so in this model, it takes 4 simple inputs. So we can place in a DEM, a flow initiation point, a total volume to be released, and as well 2 flow resistance parameters. And in taking these inputs, what ProDF can give us is in seconds to minutes, an inundation map of the inputs that we've provided. And so taking this further, how applicable is this to the tailings dam world and to known failures where we have this information of? And so let's give that a try together. So we're going to step through the case study calibration that we conducted for the Fujao failure in 2019. And so what we have on screen is a coarse 30-meter globally available DEM that we've used for the work. We're next going to pick our point of flow initiation, known as this is a failure case, and as well the volume of outflow released. So in the case of Fujao, that was 9.6 million cubic meters of material. And so because we know the initiation, because we know the outflow, we're able to perform this calibration to understand what our flow resistance parameters can be. And in conducting this, we found that this was a challenge of the model. These calibration values can be very sensitive. So we have tau, which is going to be our yield strength, and we have chi, which is going to be our flow resistance parameter. And so because we're at this calibration stage, what we did is we ran this model over a range of these parameters so that we could understand how the model accepts these resistance parameters. And through multiple iterations of this for the Fajau case, we were able to calibrate the case to a chi of 10 and a tau of 45. And in this case, that gave us the best representative model where we had 75% overlap of the event. And then we can also recognize that within this calibration stage, there are areas where the model maybe wasn't as calibrated. So we had 24% false negatives. So areas where in the actual historical event, our model didn't capture flow in those areas, and 20% false positive, so areas where our model actually inundated outside of the extent. Overall, we are happy with this result. However, we're going to note here that this is where the work is going to continue as we begin to develop this tool. And so this calibration stage is really key for us in understanding these fitting parameters and the flow resistivity parameter. Especially when we move towards doing this for more than, we've only done 2 historical cases at this point, so expanding out this knowledge to multiple case studies. And so in this proof of concept model, let's run through from the top what this screening tool could look like from the point that we have it at this spot. And again, we're going to walk through the Fajau case. And so going back to our probabilistic distribution of release tool, in this tool, we're able to put in our user-defined site factor, site-specific factors so that we can estimate what the probable volume of release could be. But even further on the right, what an output we're getting from that is an understanding of our outflow distribution that is possible in this event. And we're able to take all of those possible outcomes and put them into ProDF. So what we're seeing on screen is ProDF running 100 different cases of these probable outflows and giving us an understanding of what that flow looks like. And so now on screen, I'm able to understand what my 95th percentile looks like and compare that directly to what my 50th percentile looks like. In future, we're also looking to see, okay, if I have specific site assets of concern, I can put those on the map and understand how outflow affects those assets that I have in this failure plane. For reference, the red outline on screen is the inundation of the Fajau 2019 failure, and it's representative of a 99th percentile event for the case of this dam. And so we can recognize that this model did a good job with those dark, deeper purple showing that 90 to 100 percentile volume outflow. And so this was a proof of concept model for us at this stage, so we can understand, going back to that risk equation in our mind, that if we can understand that there's a probability of failure, that there's an associated probability of outflow given that failure, we can then assess all of those probable outcomes in ProDF, which allows us to get some results in a few short minutes to visualize what this risk could mean for our site. And so in summary and moving towards our next steps, ProDF was successful in replicating these bulk behaviors for the historical tailings dam failures, and the one we've looked at today, Fajau. And then in this model, it was capable of generating these hundreds of inundation extents in approximately 5 minutes. And where we'll be leading with for the work is that there's the need for future calibration with a diverse set of case histories so that this will improve ProDF's reliability when we move to those uncalibrated or hypothetical failure events. And then again, integrating this tool into a downstream asset data set to enable us to look at this screening level risk assessment framework throughout the work. And I'd like to thank everyone who has worked on this. It's been a big group that has pulled this work together, so thank you. And any questions can be directed to myself or Brad.
Thank you, Meg.